Okay, so I can skip this and sort of give my introduction. I'm going to go ahead and begin by kind of introducing a little bit of my research and work because since I'm a little bit of a diverse character, I think. The following set of images is really a matrix of a cross-section of the past 5 years of my research-based design practice with an interest in how technology, craft, and materials come together in ways that explore the boundaries between design, architecture, and other disciplines, specifically material-based computational strategies, supporting the integration of form, material, and structure by incorporating physical form-finding strategies with digital analysis and fabrication processes. Projects really range from exhibition design, installations, furniture, material research, functional art, and architectural projects. Um, Today, I'm going to really focus on a set of relatively new research projects in a rapid-fire series of slides looking at bio-based material and additive manufacturing through identifying industrial material waste streams, focusing on topics of sustainability and biocompatibility, functional gradation, and bespoke and site-specific design. The opportunity to overcome environmental challenges and promote responsible material management in the construction and architectural industries, with an intent to minimize the environmental impact of construction activities and promote bio-based and healthy material practices and sustainability of our built environment. So I'll kind of unpack kind of what all these kind of terms mean throughout the presentation. I'm really going to start by kind of outlining the discussion on the specific materials being used and developed, my geometric strategies, AI influences, and the resulting applications. Just to kind of name a few of the materials, I'm looking at stone, wood, seaweed, coffee. In terms of computation, things like minimal surfaces, vaulting, stereotomy, and specifically additive stereotomy. AI influences look sort of at the text-to-image based AI. There is some sort of development of collaboration with Google Colab and SOMs, and applications looking at pavilions, architectural elements, furniture, and products. So when identifying waste streams, I started working with stone since I have a background in my professional career working on many projects throughout the years. I currently have formed two industrial partnerships, one with Concrete, a Dutch-based printing company with capabilities of printing stone, and Marvel Labs in the US, who are developing binders and glues to print with a wide range of materials, so things like coffee and seaweed, as I mentioned. We are working directly with major stone companies in Italy and Florida, specifically using limestone, marble, and oolite limestone, a native material here in South Florida. Oolite is a coral-based limestone, usually found on coastal regions. Let's see, during sort of processing waste, so during cutting, shaping, and finishing, stone companies may generate 20 to 30% waste from each stone block. This waste consists of dust, slurry, offcuts, and fragments. For a typical medium-sized stone company processing 10,000 tons of raw stone annually, 2,000 to 3,000 tons could end up as waste. Coffee is a sort of retained from companies like Starbucks and other kind of local suppliers. Seaweed is collected from the beaches here in South Florida, and sawdust from home construction and sanding factories. So really my approach to sustainable design is driven by three different methods. Use a minimal amount of materials, do not produce waste, and prefer to use existing materials rather than virgin material. For the geometric strategies, I'm developing computational workflows using mathematical minimal surface geometries. Minimal surfaces are surfaces that have the least possible area while spanning its edges. Minimal surfaces often appear as natural forms, like soap films spanning wireframes, because they distribute tension evenly across the surface. The research utilizes digital technologies, structural analysis tools, and AI, allowing us to really build optimized, computationally designed shell structures and architectural elements, leveraging additive manufacturing technology. With early research projects, I was interested in using language as a design method through novel artificial AI text-to-image tools. These new tools for a unique opportunity to really blend our dreams, experiences, thoughts, and technical prowess with a personal touch to elevate our architectural design process. The future of material practice in manufacturing has made it possible to achieve aesthetics of great complexity with relative simplicity, offering a unique chance to delve into the history of architecture and provoke new possibilities of form and ornament. And the final applications are a range of projects that have either already been completed and exhibited around the world or are currently in process of being constructed. So we'll look kind of at the range of the scale of the projects from artifacts all the way into something as a looking at a pavilion scale potentially. So why stone? Stone is a biomaterial. Stone is natural and a naturally formed material. Stone is not an endangered material. Types of stone are finite or a limited resource, but we know our Earth is made of stone. Stone is also the ancient material that has shaped architecture since the beginning of time, and we consider it the forever material and proven to stand the test of time. The industrial waste created by large-scale quarrying operations, various fabrication and cutting processes, result in each manufacturer around the world to have tons of stone waste each year. Our objective is to tap into these waste streams and produce additively produced architectural elements or build without harvesting, again, virgin materials. So what kind of started this for me is the kind of middle image in there in the group of images, the coral table. This was a project I produced maybe 5 or 6 years ago. And it was milled from a solid block of stone. It took something like 16 hours a day for 1 week straight of robotic milling, plus another 2 weeks of hand finishing. And it had really a tremendous amount of waste because it was carved stereotomically. So after this project, even though it was a bespoke piece, I realized that we had to work differently. We couldn't continue down this sort of path of producing so much waste. And so I started looking and searching for alternatives until I found companies like Concrete, who work through biomass printing, who were able to take this material and develop a binding system for it. So it started the topic of additive stereotomy, which aims to showcase the integration of additive manufacturing technology and ashlar construction through a novel 3D printing stone fabrication process, a creative and imaginative design process that evokes a sense of modernity and innovation in the architectural and construction realms, while also addressing the critical need to honor the precious nature of stone as a finite resource. By acknowledging the material's symbolic and spiritual connotations, we continue adding depth and meaning to the built environment. This approach harmonizes human creativity with the beauty and strength of the natural world, ensuring that we uphold the cultural significance and aesthetic appeal associated with the material stone. So biomass printing is an additive process that uses organic, renewable materials, in this case, limestone and marble powders, combined with non-toxic binders. 3D printing is an ideal method for producing the complex curved geometry of these projects, and Concrete's Armadillo 3D printers have been employed for this purpose. Concrete specializes in binder jetting technology, a 3D printing technique where successive thin layers of powder are deposited within a machine. For each layer, a binder is selectively jetted to form a cross-section of the 3D model. At the end of the process, a solid printed shape emerges, encased in loose powder that wasn't bonded during printing. After retrieving the printed part, the excess powder is removed for reuse, resulting in a zero waste process. So I'll kind of unpack that over a few videos that we'll see. But this is just kind of a general slide that we see a bit of the production process and some projects that are coming off right now in stone and things that have already kind of been produced, like the upper images, which is a vault. Just another video of a particular stone panel. So we're able to kind of produce parts, with the same compression strength as a natural block of stone right now, or almost as close. So this is really the kind of exciting part of this material. The following project timeline really outlines the research progression of working through several kind of research challenges, from material development, creating procedural modeling workflows, to translating AI images into 3D models, and transitioning from sort of scale artifacts to one-to-one construction prototypes. So Gothic Reimagined is really the world's first collaborative AI 3D printed stone artifact. I developed a set of prompt rules in order to distort, split, and rearrange Gothic elements into a given space. Some of these rules were stylizing as opposed to realistic representation, schematic characterization of accentuating certain features. The third was dislocating split details, and the fourth, an illogical transformation of details into new Gothic representations. I think what's important, however, is to note the essential body is apparent. and to some extent, the relationship to one another is maintained. The final image interpretations were a dynamic flow or reorganization of material elements that appear taken from an earlier construction project, but reinvented and preserved as a new novel structure. The next project is Technovault, which is a prototype for a pavilion currently being developed to be stereotomically printed from discrete ashlars. And the final was Lithic Mirage, a kaleidoscopic 3D printed column structure that evokes the concept of visual deception of a mirage through a captivating illusionary effect. In the design context, Mirage suggests an artifact that questions the boundaries between reality and illusion, inviting viewers to question what they see. This effect further accentuated by using generative AI to embed a new architectural aesthetic into the surface. The structure represents an illusionary monolithic limestone figure evolving from a cloud of upcycled stone powder, achieved through innovative printing techniques that we've kind of mentioned before. And Lithic Mirage really invites exploration of material and perception, encouraging viewers to kind of ponder the boundaries between tangible and intangible, real and imagined. Ultimately, the structure blurs these distinctions, challenging conventional notions of materiality and inviting viewers to experience a captivating sort of visual deception within the context of a lithic form. You're going to kind of watch this is kind of an overview of a video we produced for an exhibition. Kind of goes through the full process of how we began to think about it as a geometry, how the modeling is broken down, and then how we integrated the parts into a printing production process. This is kind of the computational workflow of working with minimal surface geometry. We developed kind of a procedural method of being able to take multiple geometries and begin to kind of cut them together, go through automated bridging of the kind of mesh structure. This allows us to find the optimal shape that we're looking for. So we can kind of move forward a little bit. So we're working with an Italian limestone company called Pimar. Pimar is one of the largest limestone producers in Italy. They're located in the south region of Bari in the Puglia region. Really an amazing company. What we're seeing now is the binder jetting process. So you can see that each kind of successive layer is being added, and then it's essentially depositing a binder-based solution. So this is an all-natural material. It's completely healthy. There's no like toxic resins or any kind of VOCs associated with the material. Really trying to move to more bio-based and low VOC or no VOC products in what we're trying to do. This is just the final geometry. Just kind of in production now. So Technovault really aimed to showcase the integration of additive manufacturing, again, in ashlar construction, deploying a relatively new concept, additive stereotomy, a departure from the traditional stereotomy of vaulted or shell construction, historically cut from discrete solid ashlars. Instead, this concept considers constructing from discrete ashlars through 3D printed blocks. This gives us the ability to embed joinery, embed any kind of connection details. It's also very advantageous of us to reduce overall costs because we're not relying on kind of specialized labor to kind of sculpt and edit the material. The design intent really harkens back to kind of famed Italian designer Pier Luigi Nervi, and his kind of profound impact of his concrete shell structures have had on architecture and construction. Really begin to ask questions about how this method of construction can showcase efficient ways of distributing loads that emphasize the strength and flexibility of stone construction. We'll continue to strive for a structure that is not only an elegant and innovative form and an experience for the user, but also has a high strength to weight ratio, accommodating the creation of large open spaces with minimal use of materials. I also evaluate the important work of my PhD mentor, Giuseppe Fallicara, a leader in stone and stereotomic construction, where he builds up complex stone structures from these kind of discrete stone ashlar blocks that we see here in the image. By acknowledging the material's kind of symbolic and spiritual connotations, we continue adding the depth and meaning to the built environment. This approach harmonizes human creativity with the beauty and strength of the natural world, ensuring that we kind of uphold, again, the material's cultural significance. This is something that's kind of really important to several cultures, specifically the Italian culture, is where I really learned about stone in my PhD. So the idea of this project, we're really trying to create an innovative pathway to not only embrace technology and construction, but also to honor and preserve the precious nature of stone as a resource. The future development of this research looks to construct through a large kind of scale additive construction. So we're really trying to evolve, past these kind of these artifact or these kind of structural elements and really move to the one-to-one scale right now. What we had to do to achieve this was work with the company to design a printer that moves beyond kind of this kind of small format or desktop scale. And now we have a printer that can print 3 meters by 2 meters by 1 meter if we really want to. Obviously, weight becomes an issue. True stereotomic construction is made up of smaller parts and pieces. So we just need to be able to produce blocks that are maybe 1 meter by 1 meter or even smaller. This is really the goal and objective right now. This is just some current kind of proposals that we're looking at to kind of combine the traditional stereotomic principles of layering kind of stacked parts into complex figures, but only through additive processes. So instead of beginning the process with the block, we're starting with particles or powder. This kind of takes me to another collaboration now with Marvel Labs. So kind of completely different material system. In this case, we're taking raw materials of coffee, wood, and seaweed. And through this ability, we're able to kind of identify these various waste streams that are kind of more kind of personal or more local. Sort of coffee is something that we interact with almost every day, especially here in the US. Seaweed is something that is very much impacting, I'll turn the volume down, very much impacting coastal regions and also here in South Florida. So I think this idea of beginning to work with seaweed came about once I moved from New York to South Florida. We had really a time when the heat was very high and we had a lot of sargassum or seaweed wash up on the beaches and it became very problematic. This is kind of an interesting image because you see how dense it is. And typically here in South Florida, they clean the beaches daily. And so this is what washes up after one evening. So you can imagine the amount of seaweed that's washing up on the beaches every day through a certain period of time during the year. So here's essentially a video of the increase of seaweed over the last few years. And what we have is scientists estimated that there were 11 million tons of seaweed just in the seaweed belt in 2023 alone. So if left alone, this material can really create some kind of health risks to the community. I think what Marvel Labs has done is really impressive because they've really developed a kind of a workflow or a method to take this material and to dry it out and to grind it into a usable powder. We are really actively working on a range of lighting and small scale furniture objects that can be produced with this material. Again, Marvel Labs is looking at kind of breathing new life into discarded resource of wood. So every year, more than 15 billion trees are cut down to build homes and make furniture. As a result, millions of tons of waste are generated annually. While a small portion of this waste is sort of recovered, the majority of remaining sawdust is either burned or sent to landfills. So again, the strategy here is to kind of begin to rematerialize the material and create highly sustainable and high volume wood products. Coffee. So Americans consume an estimated 491 million cups of coffee every single day. This figure reflects data showing that around 66% of American adults drink coffee daily, with an average daily intake of 3 cups of coffee per drinker. Coffee remains the most popular beverage in the United States after water, and demand sustained by cultural habits, workplace consumption, and a growing appreciation for specialty coffee options. So an estimated 2.5 to 3 million tons of wet coffee grounds ends up in U.S. landfills each year. And so coffee grounds are particularly problematic in landfills because they release methane, a potent greenhouse gas. So trying to work through a number of kind of methodologies for how we work with these materials. Obviously, the challenge is um, working with a bio-based binder and putting constant load or constant use of these materials or having them in the element becomes kind of problematic. So we're working through ways to refine the surface quality, but also work through finishing options. So this first collaboration is with my colleague Natalie Alima. She's a computational designer with Adidas. We're developing this idea called the bioscaffold column. It's a structural component designed to mimic natural porous scaffolding found in biological, excuse me, organisms in architecture and structural design. Bioscaffolding columns offer a sustainable biomimetic alternative for load-bearing structures. They can enhance indoor air quality, serve as green walls, or produce insulation while supporting the weight of architectural elements. Functionally gradient design is a method that we're trying to employ here, where 3D printing allows these columns to vary in density, porosity, and composition throughout their structure, enabling customization for specific applications. So in architecture, this could mean stronger, denser materials near the base and lighter, more porous materials towards the top. And I won't get too much into this, but this is just, again, kind of showing, again, how we generate the computational side and the form making side. Just a bit of a more in-depth video of that. Since I'm kind of running short on time, I'll kind of move to how we're trying to, or actually not trying, but we actually are working through methodologies of electroplating these parts. So this is kind of common, or what we saw common in some early plastic-based FDM prints. But what we found is that, adding this extra layer of metal over the material is actually highly effective for both coffee, seaweed, materials. Wood can essentially be left alone. It's a little bit more robust in terms of its material type. But the coffee and seaweed work really well if they are electroplated. And once we've added that kind of a surface finish, they hold up really well to corrosion resistance. And then they have a much more kind of desired surface finish and aesthetical appeal to them. So we can finish some sort of copper, nickel, chromes, things like that. It was kind of exciting what we're able to do there. And again, so as I mentioned before, there was a kind of a unique chance to kind of delve into the history of architecture and provoke really new possibilities for form and ornament using these kind of new AI-based tools. This represents really an initial foray into the exploration of a novel architectural aesthetic using AI text-image technology. However, the true authorship contribution lies in the development of a workflow that translates images into 3D models and subsequently into material aggregates for production. As we kind of delve into the details, a distinct understanding emerges, contrasting with mirror images. This presents a unique opportunity to kind of blend traditional material craftsmanship with digital technology and creative AI, paving the way for kind of innovative architectural expressions. While we are still kind of in the early stages of fully grasping the potentials of these new AI tools in design and architecture, it's evident that these avenues we can delve deeper into the creative possibilities and push the boundaries of architectural expression. So this is really kind of the early kind of generation of kind of integrating AI into the process. And this is really where we are with it now. So now we're kind of developing a methodology of creating a series of products, specifically this furniture piece. This small kind of console cabinet was one of 350 images that were generated for the project. And the client had the ability to have some creative input by both selecting from the library of images, but also selecting how they would like the pattern to be mapped into these specific marble printed doors. So we're kind of in the final stages, and you're seeing a kind of a glimpse of our process of creating a procedural kind of workflow to translate any image into any size cabinet door. So you could, if you wanted to kind of reclad your kitchen, or you had an IKEA Billy bookcase or something like that, you could come into our system, choose a particular pattern, choose where you would like that pattern to be taken and mapped into that specific size door, and it would fully automate that process of integrating the hinges, integrating the size of the door, the depth of the pattern, and then it would output a final kind of mesh file type that would go directly to the manufacturer for production. And this is my final slide. So these are right now are just kind of rolling off the printer as of a couple of days ago. So we're seeing that these are printed in marble, powder waste. Each one takes only about 2 hours to produce. So a very minimal amount of energy going into the production, a very high amount of resolution. Again, this is something that we could never produce by through a hand fabrication process or even through robotic milling or any kind of CNC machining. So the additive process really gives us an advantage for a high degree of articulation, but also a really fast means of production. I'll stop there. Thank you.